Hi guys, Buildzoid here, and welcome to the first of the Z690 motherboard PCB breakdowns. Today we're taking a look at the Gigabyte Z690 Aorus Pro, and some of you might be wondering, why are we taking a look at this board? Did Gigabyte not send you any other motherboards, Buildzoid? And the answer to that question is, no, they did send me other motherboards. They sent me a Z690 Aorus Extreme, which can be simply described as a generic high-end motherboard with an insane price tag. They also sent a Z690 Aorus Master, which is another generic high-end motherboard with a less insane price tag. Actually, that one kind of has a reasonable price tag for what it is, right? Like, generic high-end motherboard. Under $500, actually kind of sensible, because that's kind of where generic high-end motherboards have been in terms of prices for a very long time now. Everything above that is steadily less reasonable as far as I'm concerned. Anyway, and they also sent along the Z690 Aorus Pro. And when I pulled this board out of the packaging, this is the board where I went, oh my god, I can't believe they've done this. And by that, I am referring to the postcode. Yes, they've added a postcode to the Z690 Aorus Pro, making it the cheapest motherboard on Z690 with a postcode, because this thing is at $330, and the next motherboard I'm aware of that comes with a postcode is $400. So, yeah, congratulations, Gigabyte. This is, like, I love postcodes a lot. Like, to the extent that I've literally recommended the ASRock B550 Steel Legend pretty much just on the basis that it has a postcode. It is the cheapest B550 motherboard with a postcode, and that is a good enough reason to buy it as, well, you know, like, obviously also has a decent VRM, but the highlight feature for me with that board is it has a postcode, and it costs less than everything else. This board does the same thing. It's got a postcode. It's also got a decent VRM. We'll get to that. But unlike the Steel Legend, it actually has even more fun overclocking features. So let's go through those, and there's actually just one of them. You do get some troubleshooting LEDs. These are totally redundant because, you know, there is a postcode. Just learn to read the postcode. It'll make your life a lot better if you do a lot of overclocking. And then there's this button down here, and that is not Q-Flash, because Q-Flash is over here. That's the button that allows you to update the BIOS of the motherboard without even having a compatible CPU. This, on the other hand, is Gigabyte's rebindable reset switch. Literally my favorite feature about their Z590 motherboards, because you can rebind that button to be like an RGB on-off switch, a regular reset switch, a go-to BIOS switch, and it can also act as a safe boot button. Now, on the early release BIOSes that I was using, or the pre-release BIOSes I was using, that button hasn't actually worked as a safe boot button at all. But they had this working on Z590, and I don't see any reason that they can't get it working on Z690, because Z690 doesn't have its own built-in automatic recovery system, unlike AMD motherboards, which is why Safe Boot doesn't work on AMD motherboards ever. Whereas on Intel, it's just a matter of getting the, you know, BIOS set up so that it works properly. So I imagine by, like, BIOS update F6 or something, this will hopefully be working, because currently it doesn't work. But the funny thing is, like, this board is already in, as far as I'm concerned, a league of its own by being the cheapest motherboard with a postcode. Once they get that safe boot button working, it's like, what else could you ask for? Like, if all you're going to be doing is overclocking, what more could you want from your motherboard? You have safe boot, you have a postcode, you've got a VRM that is capable of running any CPU you can put into the socket. I guess you could, you know, argue that it would be nice to have a dumb dual BIOS function. Which for, like, I don't know why it's so hard. Like, Gigabyte has this really weird, Gigabyte and dual BIOS is weird, okay? Because Gigabyte has basically two ways of approaching the BIOS configuration of their motherboard. Single BIOS, which is what we have on this motherboard, and this is fine. This is nice and simple. It doesn't do anything weird. You don't have to worry about it. Then they have automatic dual BIOS without switches, which is obnoxious as hell, and literally a reason that I don't use certain motherboards that I have from Gigabyte. Is just like, I refuse to deal with that. It is so annoying. And then they have automatic dual BIOS, but with switches, so that you can turn off the automatic dual BIOS function, which is cool and all, but that is, like, more expensive to implement. And a lot of people don't read the motherboard manual, and they don't turn the automatic dual BIOS off. And then they get very confused when their BIOS settings disappear after a few failed reboots. And it's like, okay, so In the interest of idiot proofing, I think I'll take single BIOS because for whatever reason, Gigabyte is just incapable of implementing a dumb dual BIOS system with just a switch. Honestly, if they just offered the motherboard with a socketed BIOS chip and a spare BIOS chip in the package, if the board came with a spare, if you had a, socketed BIOS chip and then a spare BIOS chip as a part of the accessories for the motherboard, that would technically be a dual BIOS implementation. That is like not obnoxious because you could just flash different BIOSes to each BIOS chip, but either way, single BIOS is fine. It would have been nice, it would have been a nice addition to have like a simple dual BIOS system. But considering this is Gigabyte, I am glad that they didn't put the automatic dual BIOS on there. I'd rather have this than the automatic dual BIOS. Anyway, let's move on to the rear I/O. And here we can see more signs of Gigabyte listens to my videos way too much because this has 12 USB Type-A ports, which I'm a big fan of. I love this rear I/O, but I imagine some people might be kind of annoyed that they've removed some of the audio ports to make space for all of the USB ports. So yeah, personally, I have zero issues with this. USB ports are awesome. You can, if you need more, you can just get a USB audio card, if you want, some better audio configuration. So personally, no, I think this is a win. And you do still get, I believe that's the optical out, the SPDIF out right there. I think that's an optical standard. I'm not sure. I don't pay that much attention to onboard audio, so yeah. Anyway, I love USB Type-A ports, and we've got a ton of those, so I'm very pleased with that. Other than that, there's Intel Wi-Fi 6, Intel 2.5 gig LAN, and, you get a display output for the iGPU, which, if I don't know that you, I'd say that's a waste of space, but sometimes some people use the iGPU, so, same as some people sometimes use the onboard audio. I'm just not one of them. Anyway, let's move on to the... Oh, I guess I should have also mentioned that there's 4 M.2 slots. Yeah, it's got 4 M.2 slots. 3 of them are hiding under this plate right here. I think actually you can see them from the back. Yeah, you can see them right there, right? There's your 4 M.2 slots. And now we can talk about things I actually care about, which is things like the power delivery. And we have a whole lot of power delivery here, because Renesas has now just I'm pretty sure this chip came out with the Z5, was first featured on the Z590 Godlike, but I haven't bothered to check my notes, so I'm not 100% certain about it. Either way, this is a monster of a voltage controller from Renesas. This is the RAA 229131. A 20-phase voltage controller with dual outputs. So it can handle, and here it is running as a 16+1. 16 of those phases are for vCore. The +1 is for the iGPU over here. And did I put the division down here? I didn't put the division down here. So there. And this right here is VCC in. Because the 12th gen CPUs do have an integrated voltage regulator that generates some minor voltage rails like power for the L2 cache of the E-cores and VCCSA and some other voltages. And yeah, so we've got a VCC in now instead of a VCCIO, VCCIO2, VCCSA. You can kind of see why Intel ditched that, right? You had 3 tiny voltage regulators. Now you have one. A bigger voltage regulator that handles all of those rails, because you can just use the integrated voltage regulator to generate all the sub rails from that. So that makes things a little bit more simple on the motherboards, and especially I assume in laptops it's a lot more convenient to have a setup like this instead of the old version, instead of the old configuration where you had 3 different memory controller rails, where now you have one. And it's not really a memory controller rail, right? It's VCC in. But anyway, so yeah, vCore is a 16+1 phase monstrosity with no doublers or anything, because we've just got this RAA 229131 20-phase controller from Renesas. So yeah, this is literally the latest and greatest digital controller that Renesas makes, as far as I'm aware. And it is really common for Z690 motherboards to use this controller, and consequently it is very common for Z690 motherboards to have absolutely stupid numbers of power stages and phases. This motherboard really isn't that high up there in terms of the phase count, but the thing is, it's great and all that Renesas has this fancy new controller that does all these phases. the CPUs don't pull that much power. They pull more power than a 5950X, but the thing is, they really don't pull much more power than like a 10900K or an 11900K did. And they're somewhat more difficult to cool. So you really don't need super insanely high phase counts. Honestly, even these 16 phase is very well into the territory of like, yeah, it'll power literally anything that you can put into the socket. And that's because this 16 phase is using a bunch of ISL 99390s. These are 90 amp smart power stages from Intersil, which is owned by Renesas. So, like Renesas controller, Renesas power stages is sort of the better way to put it. But these still use the ISL naming scheme. So I go and call them Intersil, even though that's not really a thing anymore. Either way, 90 amp smart power stages. Smart power stages are smart because they integrate current monitoring, temperature monitoring, and a bunch of safety features like over current protection, over temperature protection, and some other stuff. And yeah, with 16 of them, the VRM's theoretical efficiency is the efficiency of the power stages is absolutely ridiculous. We aren't accounting for power losses in the inductors or the power plane with these figures. So at 1.2 volts, 500 kilohertz switching frequency, the power stages, when pushing 200 amps of current, which is very achievable on a 12900K. That is a very easily done amount of current draw. It's it's very easy to hit this. It's not that easy to cool it though. 200 amps, the CPU will, the power stages will produce about 15 watts of heat. Which is like, that's great efficiency right there. Like it basically, if you can just get if the heat output is less than the current output divided by 10, you've got good efficiency. That's like a really easy cheat for that because, whatever. We won't get into the math because I'll probably screw it up right now. Anyway, 300 amps output, the VRM will produce about 23 watts of heat. The peak of the efficiency curve for this VRM is somewhere between 200 and 300 amps, by the way. So that's why I didn't bother with like 100 amps heat output, because it's a 16 phase. There's just no point in discussing, less than 10 amps of current flowing through a 90 amp smart power stage. This is just like dumb as far as I'm concerned. Anyway, 400 amps output. The funny thing is, like, you're not really going to, you're just not going to be exceeding 300 amps output current. Mostly because you won't be able to cool it with a 12th gen, like on a 12th gen CPU. So yeah, like this is sort of the current range where if you're pushing a 12900K, and I have to specify 12900K, because if you have like a 12700K, and the E-cores really don't push that much, like don't pull that much current either. They're also not that fast, so but they don't pull much current, so you don't really have to worry about the E-cores too much. So if you have like a 12600K, this will actually just, this is super mega overkill if you put a 12600K on this. And even for like a 12900K, this is still more than enough power delivery. So anyway, 400 amps output, it'll be producing about 34 watts of heat from the power stages, and 500 amps output, the power stages would produce about 46 watts of heat. So, really great efficiency from this VRM here, but I think a lot of people will remember that the Z590 Aorus Pro was also, on paper, a very good VRM, and then in practice, it turned out that the power plane ran insanely hot. The VRM actually also ran insanely hot, mostly because Gigabyte kind of... the thing about the VRM heatsink on the Z590 Aorus Pro is that compared to the Z690 Aorus Pro VRM heatsink, it had real fins in it. The funny thing about having real fins in your passive heatsink is that they're normally far too dense for passive airflow. So with the Z690 Aorus Pro, Gigabyte ditched that old heatsink design, which didn't work. It looked like the thing is, it looks really impressive because it has all these really fine fins and everybody's like, oh my God, it's got real fins. But then you actually test it and it's just like, well, it overheats. So useless. This, on the other hand, is just sort of brute force passive cooling. We've got a massive chunk of aluminum for the hotter part of the VRM, which is that thing. And then for the top edge of the motherboard, we've got this. Also, Gigabyte is now sinking heat from the inductors, which helps keep the power plane cool, as well as also helps keep the power stages cool. Because the inductors themselves don't really produce much heat, but they do have a direct metal connection to other things that get hot. And so the heat from the other things can sink into the inductors and through the inductors into the heat sinks, which helps, with cooling, of course. Also, we have these very large thermal pads, and Gigabyte is also sinking some of the heat from the actual 12-volt power plane into the VRM heatsinks. So, again, sort of the same idea as sinking heat from the inductors is just power stages. The black casing material that power stages have is not actually that thermally conductive. So sinking heat from the power plane over here, which actually the power plane sort of goes like that. So there's not much power plane in this area, but up here, that's more significant, where you have a decent amount of power. Like, you just sort of you have a power plane that goes basically like this. And so having the heatsink sink heat from all of this space instead of just directly from the power stages can help with thermals. So yeah, we've just got more contact area between the heat sinks and the sort of VRM than ever before for a Pro series motherboard from Gigabyte. And also, this heatsink is actually designed for passive operation, right? We've got just, it's a big block of aluminum with some very large cuts into it, which means that you have plenty of space for air to actually flow through the heatsink instead of getting trapped and steadily heating up the board. So I did run a Prime 95 test on this motherboard for an hour, and that was 1 hour with the CPU pulling about 260 watts. Actually, so 206, we'll just put 260 watts. Man, I should zoom in for that. This looks horrible because I was zoomed out. Anyway, so 260 watts, 1 hour, in a 22 degrees Celsius ambient. And the VRM ended up at 87 degrees Celsius. And that was zero airflow, right? With no airflow. So I literally went out of my way to block the airflow from the AIO from reaching the motherboard. And yeah, it ended up at 87 degrees Celsius. And that temperature reading is according to a resistor over here, which is actually a really sensible location for that temperature sensor. There are some Gigabyte motherboards where they have that temperature sensor in this area of the VRM, which is really, for whatever reason, this part of on most motherboards, this part of the VRM runs cooler than this part. And yeah, there's a few Gigabyte motherboards out there where the VRM temperature sensor is just in the wrong place. It'll give you a low temperature reading because you're miles and miles away from the actual hotspot. But I tried to check the temperature of the board with the IR thermometer that I have, and I couldn't find anything that was even at 87 degrees. I checked the power plane. The power plane was in this area was sort of approaching the 70s, but in this area you were in the 60s. So yeah, this board runs really, really cool. So the VRM, both the component selection and the heatsink design works really well, and you're just not going to have any issues overclocking any CPU that you can put into the socket. Also, you might be wondering why I was only testing with 260 watts of power draw. The thing is, so actually there's two reasons for that. One, Prime 95 doesn't like the E-cores very much. I couldn't get it to, if I had the E-cores enabled, I couldn't get the, I couldn't get the E-cores and all the hyperthreads loaded up at the same time. I could only load up 16 threads for whatever reason, which was weird. And the other issue I was running into is that if I had the CPU pulling much more than 260 watts, it would just overheat. So this was the maximum level of power draw that I was actually able to cool. The Intel 7 manufacturing process is more thermally dense than the old 14 nanometer CPUs, and so even at slightly lower power draws, they do run hotter. Even at lower power draws, they do end up running hotter because they're just denser. So that's why I maxed out at 260 watts. Though in the future, I would like to rerun this test with a better cooling system and, more heat, right? And though at the same time, I do kind of want, this is an extreme load scenario, so, and zero airflow. So it's if you actually have the board in a case. And also I was testing it on a horizontal test bench, which is still suboptimal for this style of heatsink because these fins are horizontal, right? If you have the board inside a case, even if you had no airflow, the heat would rise through the fin stack this way. in the in the orientation that I was testing the motherboard in, you get hot air coming out of the fin stack and then getting trapped against this like IO cover section, which incidentally, like that's still part of the heatsink. Like this, all of the top section of that is still functional heatsink surface area. So yeah, like this is actually a proper heatsink design. I know it doesn't look very fancy and it doesn't have real fins, as people like to call them, but this works. Like, there's nothing wrong with a really big block of aluminum as long as you cut some fins into it. So yeah, also you don't need heat pipes or anything. Like, I really like the fact that this board is just like it just has things that work as far as I'm concerned, right? Like, they didn't go out of their way to max out the available number of phases on the controller, probably to keep the cost down, right? This is still, like, this at $330, this is really not that expensive for a Z690 motherboard if you look at some of the other options out there, and especially if you're looking for a motherboard with a postcode. So yeah, and so they've ditched the heat pipe, they ditched the unnecessarily high density fin stack that doesn't actually work in a low airflow environment properly. So yeah, the VRM doesn't overheat; it'll run whatever you want. I just really like this is sort of a brute force. Like, I like it. It's not. There's not a bunch of really unnecessary fancy things on this motherboard that don't actually really work that well, right? So I really like the fact that it's like would the heat pipe maybe reduce the VRM temperatures a bit? Probably. Does it really make a difference? Nah, right? So, yeah, for that kind of reasoning, like, I like this board. It's just that a sort of no frills approach to all of and even then it's like you've got a bunch of M.2 slots. I really don't know what else you would really want from a motherboard. Anyway, so yeah, VRM will handle anything you can put into the socket. I guess let's talk a little bit about the power filtering configuration. On which note, so by that I mean like the capacitors and the inductors. So for the inductors, Gigabyte is using the 150 nanohenry inductors that they like to use when not using doublers, or when not putting power stages in parallel, because if you're putting power stages in parallel, you do need higher inductance inductors to compensate for the fact that you've put effectively your inductors end up in parallel. So anyway, yeah, we've got 150 nanohenry inductors, which is a relatively low inductance, and this is a good thing because that means you have less energy there. Well, it gives you a higher current slew rate, so it's easier to ramp up the output current of the VRM. There's also less energy stored in the inductors, so during a load release scenario, you have less overshoot because there's just less energy to overshoot with. So yeah, but this is pretty standard Gigabyte VRM design. Like, they've been using 150 nanohenry inductors on their motherboards on their higher end boards for ages. So that's nothing new. They have, however, given this board an absolutely ridiculous input filter, right? We've got these 3 bulk capacitors over here, and then these 5 up here. And the thing about the reason why I call this ridiculous is that it's not that long ago that a high-end Gigabyte motherboard would basically just have 4 bulk capacitors for input filtering, and that was it. And now we've got like what is basically, by Z690 motherboard standards, a mid-range motherboard, and it's got 8. Like, it's got twice as many capacitors as what you'd get from like flagship motherboards from Gigabyte a few years ago. So that's kind of neat. For the output filter, we're looking at standard just Gigabyte output filtering. So this is the actual vCore VRM output filter. This is for the iGPU. This is for the VCCN. But for vCore, we're looking at 10,000 hour rated Nichicon FP caps. So that's 10,000 hours at 105 degrees Celsius. And yeah, these are solid polymer capacitors that Gigabyte has been using on their motherboards for ages. So nothing new there. Also, the same is true for the input filtering capacitors. Those are also 10,000 hour FP caps, just rated for 16 volts instead of 6.3 volts. And yeah, so pretty standard through-hole capacitors right there. For the CPU socket, we do have the sort of... This is standard. Like, Gigabyte started doing this with Z490, so a mix of pulse caps and multi-layer ceramics on the back of the board. On the front of the board, some idiot forgot to take off the socket cover, so we can't see it, but the front of the board, you just have multi-layer ceramics in the socket, which makes sense because on the, electrically speaking, the multi-layer ceramics on the top side of the board are actually closer to the CPU socket than the capacitors on the back of the board, because the caps on the back of the board are connected to the socket through a bunch of vias, whereas the capacitors on the front of the board are literally on the same power plane as the CPU socket itself, right? The CPU socket is BGA, and so these capacitors are connected probably to exactly the same, copper layer, same piece of copper that that the actual socket itself is connected to. So yeah, because you can see that we just have a power plane sort of running towards the socket in this area. Well, not that clearly in this photo, but still. Anyway, yeah, so output filtering wise, sort of standard Gigabyte configuration, and it's worked really well. Like on Z490, I already had issues measuring any difference in transient response between low end and high end motherboards from Asus, Gigabyte, MSI. Like I just couldn't measure a difference. And so with Z590 and with Z690, Gigabyte has basically taken everything they were doing with their Z490 boards and just kind of gone like, well, do that but more. Right, so we've got more capacitance, more input filtering capacitance, and that's kind of it. So, yeah, voltage regulation wise, I can't imagine this having any issues. Actually, what's funny is on the Z490 boards, they were still using doublers, and it didn't make a difference, right? Like, I still couldn't measure a difference in transient response. Even between, like, motherboards that were, like, true, without doublers versus with doublers, it just doesn't, it just didn't make a difference. So, yeah. So that's the VCore VRM here, and basically, yes, you can get Z690 motherboards with bigger VRMs than this. You don't need them though, because this will do every I've got you don't need more. That's basically all there is to it. You just straight up do not need more VRM than this. This will power a 12900K unless Intel goes insane and gives us like a 400-watt CPU. Then on the LGA 1700 socket, like this VRM is going to be perfectly fine. So yeah, especially if you give it some airflow, right? Like I was testing in a zero airflow environment and it was still running at perfectly acceptable temperatures. Honestly, I kind of suspect you could probably get away with, if you had mild airflow, you could probably get away with running this VRM with no heatsink whatsoever. I might do a test of that just for fun, because yeah. Anyway, so that's the VCore VRM, and there's really nothing to complain about there. So anyway, next we have the iGPU, which is just another ISL 99390 power stage. So that's like, the thing is, I don't care about the iGPU, so that exists. So yes, you can use the iGPU. I can't imagine that it would ever max out the power stage, so that's fine, I guess. And then for VCCN, we've got very different parts going on here, because the VCCN is handled by a monolithic power systems controller, which is an well, my notes say MPS, but I think that's a mistake, because normally monolithic power systems parts are MP something, not MPS something. But either way, if you go to their website, I'm not sure you'll be able to find this controller. I think it does have a public data sheet. Anyway, MPS 2940, and this is a two-phase controller. And it seems to exist specifically for VCCN, because there's a lot of motherboards using this controller. And then for the power stages for that, we've got monolithic power system power stages, and those are MP... Yeah, see, these are MP87992s, but the controller has an S in it. I have no idea why that... I'm pretty sure that has to be a mistake. Like, because this is a normal monolithic power systems part number, and this is just weird. Anyway... these are 70 amp smart power stages, and I have no idea how much power the VCCN rail actually has to supply to the CPU, but either way, if it's outputting 40 amps, which seems way too high, because you have to consider VCCN is an input voltage for the integrated voltage regulator. It sits at 1.8 volts, right? So it's a high voltage rail that consequently doesn't have to supply as much current. So VCCN, like at 1.8 volts and 40 amps output, that would mean the CPU is pulling almost 80 watts of power for the memory controller and the L2 caches of the E-cores, which is kind of like, is probably not doing that, right? Right? It's like the minor rails aren't going to be pulling 80 watts, but either way, if somehow it was pulling 80 watts through that, 40 amps would produce only about 4 watts of heat, and that is at 1.8 volts output voltage. Well, obviously not actually 80 watts, but close to 80 watts because 1.8 volts. So 1.8 volts output voltage at 800 kilohertz switching frequency. So yeah, and also at 70 amps, it would only produce about, 70 amps would actually be kind of pushing it because 8 watts of heat is like 4 watts per power stage. Depends how much load is on the vCore VRM portion of it in that scenario, I think. Though, there's no way. There is no way that the VCC in has to supply, 100, that's over 100 watts of power. There is no way the VCC in has to push that much power. That's insanity. So, yeah, either way, if it somehow did, the heatsink would still probably be able to handle that as long as the vCore VRM wasn't also being maxed out at the same time. So, yeah, that's the power delivery on this board. And yes, you can get bigger VRMs. You can get VRMs with more fancier capacitor configurations. But honestly, this will probably do everything you ever this will probably do everything you want. I don't really see much point in, going past this in terms of the VRM configuration on Z690 motherboards, because the CPUs, they're even harder to cool than 10th gen. Or they're even harder to cool than 11th and 10th gen. So pushing those kinds of power draws is just going to be really hard. So you're probably going to run out of CPU cooling headroom before VRM thermals really become an issue. And with a VRM like this, they really, really shouldn't become an issue. You would have to be pushing so much power through it. So, yeah. And that's basically why I consider this the go-to Z690 overclocking motherboard. You've got a VRM that'll handle anything you put into the socket. You've got a post code, and eventually we'll hopefully have a functional safe boot button. And, what more could you ask for? I guess we should talk about the memory topology, but the issue is I don't have a lot of experience testing a bunch of DDR5 motherboards just yet, so I can't judge the memory topology here. I can tell you what it is, I just don't know if it's any good. It's a 6-layer shielded daisy chain, so yeah, the motherboard does use a 6-layer PCB. Also, fun fact, on Gigabyte motherboards, you can tell how many layers the board has based on that right there. It has a 1, 2, 3, and if you flip it over on the back, it should say 4, 5, 6. 8-layer boards will have 4 squares with 1, 2, 3, 4, and then on the back 5, 4. Actually, you won't even see you won't see the 2 and 3s because it's not transparent. They have solder mask over it, unlike MSI. MSI has the same kind of indicator in this area, but they have it transparent, whereas Gigabyte doesn't. But either way, 6-layer PCB. We have a shielded daisy chain topology, but I'm not going to add the shielded part to that. But yeah, it is a daisy chain. So when you're installing your DIMMs, you put your DIMM slots, you put your DIMMs in the far out DIMM slots, and it's a shielded daisy chain in that because we can't actually see any of the data lines, right? There's nothing in this area. There's nothing in this area. You can see I believe it's the command and address bus, right down the middle there. And then on the back, you can see more of the same, right? You can see command and address bus over there, but you can't actually see any of the data lines going from the memory slots to the CPU. So it's a shielded daisy chain topology. You'll also notice that we have SMT DIMM slots on this, but those seem to be standard for DDR5, probably because DDR5 runs at such high clocks that the electrical properties of the pinned DIMM slots are just not good enough for the frequencies that DDR5 runs at, because the pins basically act as a source of interference and they can cause reflections. They also have, I would assume they also have more parasitic capacitance to them. So yeah, SMT DIMM slots are just better for high-speed signals than through-hole DIMM slots. And you can see the same thing going on with the Gen 5 PCIe slot over here. That's also an SMT PCIe. That's an SMT PCIe slot for the same reason. Gen 5 PCIe runs at very, very high speeds. And so for the sake of signal integrity, no more pins. Actually, no more pins, right? You don't have pins going through the board. The thing is, you could argue that the gold fingers are kind of pin-like, which they are. But less less pin-esque compared to actual pins. So, yeah. Anyway, oh, I guess I could have also mentioned that Gigabyte is still using solid pin power connectors, so you don't need to worry about plugging in the extra 4-pin unless you're really hammering a 12900K, right? The 8-pin alone is more than enough power delivery. Like, I've been doing all of my testing with just one 8-pin because there's just no point plugging in the extra power connector. It doesn't make a difference. The 24-pin is also all solid pins. So yeah, you don't have to like, so it can handle, like, it's the, like, that's the high current flavor of the power connectors for a motherboard, is what the solid pins are. And yeah, that's the, I think I went through everything in my notes. Oh, I guess I could have mentioned that the memory, so there is a memory power rail on the motherboards still, even though DDR5 has its own. It's super weird. Like, there seems to be like 3 different yeah, you have like your DIMMs have their own power delivery. The motherboard has its own memory power delivery. It's a bit weird, but yeah. So we do have some memory power delivery on the board, and that is an NCP 3235, and that's just a integrated buck converter. And for some reason, I didn't put any details about it into my notes, so I can't tell you more than that. But you can look up the datasheet if you want to. The thing is, like, the whole idea with putting the power delivery onto the DDR5 memory sticks is that you don't require as much power delivery on the motherboard itself. So we can kind of see that in action because there's no way this has the same kind of power delivery capabilities as what you normally saw on DDR4 motherboards, which was at least 3 discrete MOSFETs. So now you just have one rather large integrated buck converter right there. So yeah, there. That's actually it, right? Yeah, we've gone through absolutely everything. Also, the video's longer than ever. Oh well, I guess that's just how that works. So yeah, the Gigabyte Z690 Aorus Pro. I consider this the go-to overclocking motherboard. Like, it has a post code. It costs less than everything else with a post code. The VRM is capable of powering anything you can put into the socket. I personally really like the rear I/O. Maybe if you care about having more audio ports, it might not be ideal. And then in terms of the rest of the feature set, it's kind of standard Z690 stuff. So yeah, you just kind of get some extra, extra add-ons for overclocking with this, and you don't get the incredible price hike that you get with some of the other motherboards that offer similar overclocking features. So yeah, I really like it. Thank you to Gigabyte for providing the motherboard, and that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, the usual YouTuber merch. Both Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you'd check them out. And that's it for the video, so thank you for watching, and goodbye.